I'm Lucianna Kiffer, and I'm presenting under the hood of the Ethereum Gossip Protocol. This is joint work with Asad Salman, Levin from UMD, my advisor at Mislove, and Cristina Nita-Rotaru. So Ethereum has historically been the second largest cryptocurrency by market cap, right behind Bitcoin. But other than just a currency, it's really a platform for running smart contracts, allowing users to implement things like voting protocols, games, other tokens, and wallets, all without a trusted third party. So the currency and smart contract use of Ethereum is built on top of layers of infrastructure and protocols running atop a peer-to-peer network. In this work, we take a closer look at that network, who is part of it, and how they participate in block propagation. So we're interested in studying Ethereum from a holistic view to better understand how all of its layers interact. This includes the application layer, which is the blockchain and its transactions, and how to interpret the blockchain. Then you have the Ethereum layer, which is how we hear about the blockchain, how blocks and transactions are sent in the network. There's the peer-to-peer layer, which is how you find people to connect with on the network. And finally, the global infrastructure that is the internet that this all depends on, so everyone's physical location and their links. Ethereum has been around for almost 6 years, and there's a lot of work measuring it, mostly focusing on what can be extracted from the blockchain, so what transactions are taking place and what contracts are doing. This is a brief list from the last few years. And then the other category of measurements are of the actual network, looking at who's in the network. And there are 2 papers to note here. Decentralization in Bitcoin and Ethereum networks, where the authors compare certain decentralization properties of Bitcoin and Ethereum. For Ethereum, their measurements are on bandwidth and latency of peer connections. And then the other paper is measuring Ethereum network peers, where the authors do more of a comprehensive study of the peers on the Ethereum network, basically breaking down the characteristic of the peers. Both of these projects, when collecting network-wide information, they perform more of a scrape of the network, where they connect to a peer, collect information about the peer, and then they disconnect. They're not maintaining long-term connections to these peers. So our goal is to maintain connections to these peers so we can collect a holistic view of the network, linking who we're connecting to with the information they're providing us. So we both receive higher level information like block propagation and observe peer connectivity behavior like churn and connection lengths. So to understand how we do this, we first need to get into some specifics about how Ethereum networking works. So starting at the bottom of the protocol stack, we first need to hear about new nodes in the network that we might want to connect to. This all happens over UDP, and it's the peer discovery protocol. This is a general purpose protocol, so we may come across other nodes running some other protocols like Swarm or Whisper or even Ethereum Classic nodes. So at this layer, we may already know someone, so we're going to reach out to them, and then we might ask them if they know about other nodes with a find node message, and then we'll get back a packet with node IDs and IPs that we can try to connect to. So we call nodes at this layer UDP nodes. And once we know some Ethereum IDs, we can move up to the RLPX layer that runs over TCP. RLPX is the protocol responsible for encrypting, encoding, and transferring messages between nodes. So we'll do a hello handshake, which includes information like protocol version, client software and capabilities, chain IDs, so we're following the same fork. So at this point, we're trying to establish that we are running the same protocol on the same chain. So we call people at this layer TCP nodes. And if all of this checks out, if we pass the handshake, then we can actually start running the Ethereum wire protocol, where we start sending each other new blocks and transactions we hear about. And so finally, we call this a peer, which is someone that has passed all of the handshakes. Again, our goal is to maintain these long-term connections with peers, so get up to that Ethereum level, and then connect the behavior from the other layers with the block propagation. So how do we collect data? Well, quite simply, we just run a client in the network. There are a couple different client options. We chose Go Ethereum because it's the most used official client, but we make a few modifications. First off, we added logging of every message we receive, which includes all UDP and TCP handshakes, when we connect and disconnect from peers, and all new block messages we receive. Additionally, we increased the peer count from 50 at the time to become a supernode. So to determine what this cap should be, we ran a client with a cap of 3,500 and found that we tended to cap out at about 1,000 peers, and that most of our peers were inbound connections, so this green line here, meaning they initiated the connections to us. This is likely because we have so many open peer slots. Less than half of our peer slots are taken up, which means that all connection attempts to us succeed. While when we're trying to peer to others who are probably running with smaller peer counts, for our connection to succeed, we have to get lucky and catch them when they have an open slot, which is much less likely. So again, it seems that about 1,000 is the cap of reachable peers. And then to understand this cap a little better, we also ran 3 clients simultaneously with different peer caps, so 500, 1,000, and 1,500. And we looked at the breakdown of the kind of connections we're making. So if they're short, they last less than 10 seconds, medium between 10 and 1,000 seconds, or long, so longer than 1,000 seconds. By seeing how many of the unique connections we make per hour, we see that with a 500 peer cap, most of the connections are these long connections. So that's this blue line. Then as we increase the cap, so we're moving to the right, we see the number of long connections go down as the short and medium go up. And then even more so for the 1,500 cap, where now about 50% of our connections are these long connections. So what we get is that the more peers we connect to, the more of the churn we're really connecting to, the more of that green and purple peers we're seeing. So we settled on a cap of 750 peers as both representative of the network, and as we just saw, if we undercount anything, it's that churn. And then the last modification we did was not announce a third of all blocks. So we want to announce blocks so that we're useful to our peers, and so we remain connected to them, and also to limit our negative impact on the network. But when we're talking about block propagation, we don't want to consider blocks that we influence the propagation of. So we don't announce a third of them, and those are the ones that we're going to analyze. So we ran a client in the US for 7 months. This is our main run. The bulk of our analysis is on this experiment. And then we also ran shorter runs in Asia, Europe, Australia, and Brazil to look into how location affects our results. They all run NTP, and everything was run on EC2 instances to limit external variables that we can't control for and to ensure we had sufficient hardware capacity, both memory to handle all the connections we maintain and storage for the amount of logging we're doing, which was multiple terabytes. So there is a question why we chose AWS, and though any choice is going to have its biases, we did note that about 25% of all the peers we connect to are running on Amazon machines, and that's the largest fraction from any single provider, so given a choice, this one seems to be a representative one. So looking again at our protocol stack and how we define different nodes we connect to, in our longitudinal run, so in the 7 months, we talked to 1.3 million node IDs on the UDP layer, and only 15% of those do we ever start a TCP connection with, and then about half of those pass all the handshakes and become full peers. Again, this is by node ID. We do see some evidence of IP reuse, Generally, it's a one-to-one mapping from ID to IP, but there are a handful of IPs that generate many node IDs. So looking at these counts from the IP level, we see that the majority of IP reuse is happening at the UDP level. But generally, we observe that only 7% of all node IDs and 16% of node IPs we talk to ever become full peers. And when we look at how these counts show up daily, we see the numbers are more or less stable. So really, there's a constant influx of new nodes joining at each level. So focusing just on the full peers now, let's see how we experience this churn. So if we look at the number of connections we maintain on average each hour compared to how many connections we're starting and ending in that hour, we see that in an hour we tend to start and end 3 times our average peer count. And breaking this down by the length of our connections each hour as, again, short, medium, or long like we did before, we see that the majority of our connections are actually long ones. So all that churn we're seeing on the left is due to a small fraction of the total unique peers we connect to in that hour. So a fraction of our peers are constantly reconnecting to us for short periods of time. Again, remember our goal of connecting this peer behavior with block behavior. So for the rest of the talk, I'm going to be walking down the protocol stack, focusing on some questions of interest, starting with how is mining distributed among the top miners and pools, and are they equally efficient? Do some miners appear to have an advantage over others? Then looking at the timestamps of when we hear about different types of blocks, we can look at how blocks are being propagated, both in terms of delay and number of announcements. And then the bulk of the novelty in our work comes from tying in the bottom 2 layers, so peer connectivity behavior, with its usefulness in block propagation, so the Ethereum layer. So we ask, what trends can we observe in peer connectivity? And we want to differentiate all peer behavior from those actually telling us about blocks. And then lastly, how does location play into all of this? And are there locations to run a peer where you might be at a disadvantage or advantage? So jumping right into the top layer, by participating in the network, we hear about all the blocks being mined. This includes the blocks that are part of the main blockchain. This is the history of Ethereum, the transactions that matter. But not all valid blocks share the fate of making it to the main chain. Because blocks are found every 15 seconds or so, it often happens that 2 or more blocks are found at the same time. Miners can choose to include references to these non-main chain blocks in their block. These are called uncles, and both the miner of the uncle and the miner who included the uncle get a bit of extra reward for it. And then if there's no reference to it at all on the main chain, we call it a prune. The only way to observe these prunes is by being on the network logging them when they happen. So we see on average about 6,000 main chain blocks per day, 400 uncles, and 10 prunes. And though 10 prunes a day doesn't seem like much, in our 7-month measurement, that comes out to over 2,500 blocks of wasted work where no one's getting rewarded for it. Now, if we look at who's mining what fraction of these blocks, we get this cumulative graph of mining fraction by the top miners, and we see that over 90% of all blocks are mined by the top 15 mining IDs, all but one of which are big known mining pools. And to understand this a bit better, we break down the different kinds of blocks miners are mining. So we look at the fraction of blocks mined per miner, and we see here that the top miner mines about 26% of all blocks and main chain blocks, but only about 20% of all uncles and prunes. So there's a disproportionate efficiency in mining. And we see that the top 3 miners are an advantage where when they mine a block, it's more likely to become part of the main chain and therefore get the full reward than become an uncle or prune. And another example here, we see where miner 10 is mining a greatly disproportionate number of prunes. Moving on down the layers, I'm next going to be going over how blocks are propagated. So we need a last little bit of background here, which is how nodes handle hearing about a new block. So when a client hears about a new block, they check the header of the block. This includes the proof of work, the size, some basic checks before they send it out in full to a portion of their peers. This is a square root number of their peers. And then they actually check the contents of the block. They'll add all the transactions and their state changes to their internal state, and then send out just a hash of the block to the remainder of their peers to let them know they've heard about the block. And if any of those peers haven't heard about the block, then they might ask that peer for it. Okay, so how do we first hear about blocks during our 7-month run? Well, for the main chain blocks, we see what we would expect, that by far we hear about blocks first as the full block. We do have a bit of a weird situation at the tail end of our experiments that's due to the blockchain approaching a scheduled protocol difficulty bomb, where the difficulty was being artificially increased. And if we look at uncles, we see the same behavior. There's less of them, but we're mostly hearing about them as the full block first. But prunes are a bit weird, where we're hearing about a lot of them first as just the hash. And we actually investigated this further, and we saw where main chain and uncles receive between 100 and 300 announcements per block. 70% of prunes have just a single announcement, just one peer telling us about that prune, and these tend to come in batches of hashes. And these tend to have much lower or higher block numbers. So the block numbers don't correspond to the current main chain height. So we filtered these out from further analysis, as they're not true prunes from the current position of the chain. Additionally, I want to add that when I said before that we see about 10 prunes per day, I'm not including these weird ones. Otherwise, that number is closer to 100, as we can see from the plot here. And also for the minor analysis, we didn't include these weird prunes either, because for a lot of them, we never actually get the full block. So we don't know who mined the block and if the block even exists. It could be some kind of weird spamming behavior. Next, looking at when all of our peers are telling us about a block, we take the time from when we first hear about a block to all subsequent announcements, and we get a few things here. First, that all blocks tend to peak at about 200 milliseconds. And second, the uncle and prune lines are lower than the main chain, meaning they have a longer tail, suggesting a longer network propagation time, which explains why they didn't become the main chain blocks. And we might expect prunes to have a longer tail than uncles, but since there's a lot less of them, we would expect there to be more variance in their behavior. So this may not be the case. And then lastly, we looked at if there was a correlation between gas count and block size and the medium delay of main chain blocks, and we found that there was not. Okay, moving on. Let's connect all of this behavior to the actual peer behavior. Recall that we consider a node a peer if they pass the TCP handshake. Then we call a peer useful if they ever tell us about a block. And we see about 28% of all the peer IDs we come across and 42% of all the peer IPs are useful. And then we call a peer a first announcer if they're ever the first to announce a block to us. And we see about 14% of all peer IDs and 17% of all peer IPs are first announcers. And this is a smaller group, so we did wonder if we could tie first announcers to particular miners or pools, but we find that no peer announces more than 6% of a miner's block to us, which is probably good for security reasons of pools. So looking at these three types of peers, we compared the CDF of how many days they are online and their average connection duration. So we find that the useful and first announcers tend to be online for more days and tend to stay connected for longer. So here we see that all peers, that 30% of all peers ever show up only one day, while about 80% of the first announcers show up more than 10 days. And then on the right, we see that the useful and first announcers are also maintaining longer connections than all peers. So again, peer usefulness has a strong correlation with how long and how often we connect to them. So next we look at where these peers are. So all our peers and our useful peers are pretty evenly split in Asia, Europe, and North America. But we're mostly hearing about blocks first from peers in North America, which is also where we are. So the question is if that's because we're in North America or because the miners are. So this leads us to the last bit of the talk, which is on how our location affects how we hear about blocks. So we ran 3 clients simultaneously in June of 2019 out of Virginia, Seoul, and Frankfurt. And we saw that all 3 clients primarily first hear about blocks from their same continent. And this is primarily strong when they're the first of the 3 to hear about a block. And all 3 locations are pretty even when it comes to which one hears about a block first. So the question now is that because miners are evenly split among these 3 continents, or again, just because that's where we are? So to further explore this, about a year later, we ran another experiment, this time adding nodes into locations where we weren't seeing a lot of peers. That's Sao Paulo and Sydney. And we find that the first 3 locations continue to behave the same, where they're first hearing about blocks from near to them. But Sao Paulo and Sydney are way more split, with almost 50% of Sao Paulo's first announcements coming from North America, and 50% of Sydney's first announcements coming from Asia. And we also find that when we compare all 5 machines, Sao Paulo and Sydney together are the first to hear about blocks about 3% of the time. So they're clearly at a disadvantage. So to summarize our results, we ran an instrumented version of Ethereum's Go client Geth to collect longitudinal metrics of the network. And our findings include extensive peer churn in both number of unique peers and connection lengths, also minor centralization and disproportionate efficiencies. We also find that most announcers are long-lived compared to the average peer connection length, with first announcers maintaining the longest connections. And that announcers are diverse. We weren't able to link peers to particular pools. And also that there's pretty quick network-wide propagation with delay peaking at 200 milliseconds, and our locations exhibiting at most about 100 milliseconds delayed from each other for most blocks. But we do see evidence of location bias, in which vantage point is the first to hear about new blocks. Really what we find is that there's more to understand about this network, both what the majority of peers who aren't participating in block propagation are doing, and the effect of so much churn on the stability of the network. Please check out the paper to learn more and reach out with any questions.